Greetings and welcome to the video on standardized mean difference. So now we're going to introduce the concept of standardized mean difference. Let's make that a little bit cleaner. Mean difference. So this is an effect size again, and this time I'm going to break this up into two shorter videos, standardized mean difference, and we're going to start with the independent t-test, and then we'll do a separate video on the dependent t-test. Okay, so if we're using the raw when the measure is inherently understood or widespread, then we're going to use the standardized mean difference used when not inherently understood. Measure or not used, how do I want to say this, used in widespread fashion. Okay, so the big picture here is essentially we're going to kind of create a z-score. It's going to be a kind of a type of z-score, essentially. And you're going to get it by kind of dividing that mean difference, that raw mean difference, by something. I'll put it underlined. And if you stop and think about this for a minute, you might be able to finish this statement, because how do you create a z-score? It's a raw score minus a mean divided by the standard deviation. And so in this case, we're going to divide by some kind of standard deviation. And there's different ways to think about and calculate what kind of standard deviation we might want to use. So I'm going to kind of draw an arrow over here and say that this could be variable. Different textbooks might show you different ways. Don't particularly want to get into that. That's a little bit deeper discussion than we need to go right now. But for right now, I just want to let you know this approach to effect size, where you're using kind of a unitless value, kind of like a z-score approach, was suggested by Jacob Cohen in both a 1969 text and a 1987 text. And really what we should be doing is, and I didn't mention this earlier, but after we report our statistical results, we should both report the statistical result of our null hypothesis significance testing, but also a measure of the size of the effect, or the effect size. So we should be doing both. So what's the calculation here? Calculation for independent t-test. Standardized mean difference calculation for independent t-test. Okay, well, remember we used capital D for the raw, unstandardized. Now we're using small d, and it's simply that mean of group 1 minus the mean of group 2, just like it was for capital D. And then we're going to divide by something. In this case, it's a standard deviation. And notice it's an S. And because it's an S, it means it's a statistic. So it's a point estimate of what's going on in the population. And you'll recognize this sub p, where S sub p is the square root of this SP squared term that you calculated for the t-test. If you remember, the S squared sub p was equal to the standard deviation, or sorry, the variance of group 1 multiplied by the degrees of freedom for group 1 divided by degrees of freedom total, plus the variance of group 2 multiplied by degrees of freedom group 2, degrees of freedom total. And it gave us what was called this pooled variance that we needed for the t-test calculation. Well, now we're going to take the square root of this. Okay, so essentially SP is going to be the square root of S squared P. So let's suppose a study with the following data. Let's see, the mean of group 1, we're going to go back to this 103 again. The mean of group 2 is 100. Let's say that the standard deviation of group 1 is 5.5, and the standard deviation of group 2 is 4.5. The sample size of group 1 is 50, and the sample size of group 2 is 50, so total sample size is 100. So how do we get this S squared term? The pooled variance term. It's going to be 5.5, and we have to square that because it's the variance piece, and we have the standard deviation piece. So to go from standard deviation back to variance, we've got to square it, and then multiplied by 49, which is the degrees of freedom of group 1, which is n minus 1. So 50 minus 1 is 49, divided by degrees of freedom total, which is n1 plus n2 minus 2. So this would be 100 minus 2 equals 98. So divided by 98, plus 4.5 squared, 49 divided by 98. And if you plug and chug this, you get 20. Let me undo that. 25.25, and to get the pooled standard deviation, it's the square root of 25.25, which equals 5.024. So now we have everything we need. We've got this term, we've got this term, and this term here and here. Okay? So when you plug and chug here, you'll get D equals 103 minus 100 divided by 5.024, which equals 0.597. Now let's provide some meaning to this. When you remember again that what we're saying is we're testing the null, which says that the mean of group A minus the mean of group B equals 0. So here's the 0, our central point, and what we're saying is that here's one standard deviation, here's two standard deviations. Our treatment, right, caused caused IQ to raise 3 points, and 3 points is essentially saying we moved that group. Let's see if I can write this in here really small. We moved that group 0.59 standard deviations. We increased their score 0.59 standard deviations. And so now you can compare your effect, the magnitude of your effect, to any other study. It's a unitless convention here, unitless metric. And Cohen gave us some general conventions for kind of small, medium, and large. I would caution you to be very careful with using these, but in general, we kind of think of a small as a 0.2, a medium as a 0.5, and a large effect as a 0.8. So this is 0.8 is saying you've moved it 8/10 of a standard deviation. 0.5 is half a standard deviation. Small is 2/10 of a standard deviation. And so that's how you calculate the effect size for an independent t-test with some conventions here. So hopefully you're starting to develop an intuition for why we need both the statistical result saying that yes, this group is different from zero, and then we need some kind of measure of how far from zero was did this treatment move our folks on whatever our outcome measure was. And so you really need to have both. And so again, hopefully that's becoming intuitively apparent to you. So I hope you enjoyed this video.